Hello and welcome to our discussion of Chapter 1 on generative modeling. We'll start off with kind of the basic question, what is it? Then kind of introduce a very kind of simple idea of what a generative model might be, and then talk a bit about some of the core probability theories that go into it. Not essential you understand all of the probabilities, but it's good to have a good foundation because it helps you understand how they all work together. And then we'll talk a little bit about taxonomy, make sure that terminology and vocabulary are aligned. So what is generative modeling? Um, and it's the idea is that we take a model, and a model is a thing that is used to approximate something that's much more complex. So it's intended to represent something, but in this sort of way, you can think of it as a really complex function, for lack of a better word, not a true mathematical function, but a thing that you put something into and you get something out of. And in that regard, it kind of ties in. But when we do these models, we take training data and we basically uh, run it through a process to make it such that it is suitable for the purpose that we're using. And then we use it in a kind of a certain pattern to train the model, is the terminology you'll hear. And so in particular, generative modeling is part of machine learning, which is also part of AI. And it's all about training a model to produce new data that's similar to, but distinct from, the data that it's seen in the past. So um, we uh, we take a bunch of training data, we run it through some sort of process, and that training data is an observation. And that produces a generative model. And then we can use that generative model to essentially select a sample from it. So we have it give us some information, introducing some random noise into that sampling process. That will give us images that are similar to but distinct from those we've seen before. So it's an interesting way of creating something novel, unique, and new. And so in order to do this, we need a data set with a lot of examples. And when we're talking about most of these, especially on the topic of large language models, that size of the training corpus is immense. Think the size of the internet or bigger. It's basically all of the information that the researchers could get their hands on, if you will. And so they take that data and they do stuff to it. And one of those little pieces of information is an observation. And an observation is made up of features. And features are a thing that are of interest. So you may have heard features and feature engineering from machine learning. It's been around for quite some time. But you can say that an observation is a collection of features. And what those features may be depends upon the context. Image generation is not easy. In fact, we've, using traditional approaches, struggled with it for years. And that's because you have a bunch of tiny things. These pixels are what make up images. And there are a lot of them in an image. And so but they need to be aligned in such a way that as a whole, they make sense. And the better they are, the more likely they are to fool our brain into thinking they are what they're trying to be. And so then we have this model that's another piece of the equation that takes and introduces a certain amount of randomness to make sure that what it's generating is unique, so that it isn't going to be the same thing over and over. So there's kind of, I guess, a different way of doing things that is not generative, but is discriminative in nature. And that's about differentiating between something and something else. And that's what we did a lot of before we had generative approaches. So you'd have a labeled training set. So your data set had to be labeled. And that was a lot of work. You had to go through oftentimes by hand, and typically it was by hand, and classify things into different categories. Ideally, you would collect things that had already been previously classified just by the nature of their being. And then you would take that labeled data set that had already been classified into something. So in this case, it's Van Gogh or it's not. And we take that and run it through a model and ask the question of it in combination of, hey, what are the chances? What is the likelihood that this particular thing was created by a particular author or creator? In this case, we're saying, is this painting a Van Gogh painting? And it's more likely than not, is the example given. So the key piece with generative models, we don't have to have a labeled data set, and that's huge because that was one of the biggest costs at the time, was having to have somebody go through and generally label these things by hand. And worse yet, you couldn't just have one person do it because people make mistakes. So you'd likely have at least three, maybe some larger odd number that you would use to determine if something was something or not. And so there was lots of work that went into that sort of stuff. And so that's basically kind of a competing school of computer science was around doing discriminative modeling. But generative modeling kind of came along and exploded onto the scene, and that's not exactly the case. It exploded over the course of over a decade, maybe longer if you go back to the roots of how we got here. But over the last few years, it's been increasingly evolving. So generative or discriminative modeling used to be the only choice you had. If you were in the military wanting to know if a picture contained tanks or not, so satellite imagery, did it contain, military vehicles of some sort, you would literally have to determine, is that a tank? Is that a Jeep? Is that something else? And so it went through a lot of different approaches and work to make that work. And the odds, the likelihood or the correctness wasn't all that fantastic a lot of times. We had a few things that we were able to solve. Handwriting with convolutional neural networks, especially early on with numbers. And that may not seem like a big deal to be able to detect a picture of a number and turn it into the number. But back in the days when people actually mailed letters, the postal office had to figure out what zip code something went to on a typically handwritten letter. And so rather than having a person sit there, read it, typing it in, and so on, they literally scanned it with something and it printed the barcode on the bottom. Now it's not as big of a problem because people don't mail letters any longer. But in the days of the Postal Service being at its peak, that was one of the big wins, and it came along because of convolutional neural networks. But anyway, generative solutions take a different approach, and they did things in a different way. And they came along and turned out can actually rival, if not exceed, humans. Which is interesting as well as terrifying at the same time. So whenever we talk about generative modeling frameworks, we assume that we have observations that have been generated according to some sort of unknown distribution. So we don't know what the distribution of something is, but we assume that there is a distribution. And then we build a generative model, and we call that model CP, or a piece of model, that mimics piece of data. And if we achieve that goal, we can then sample from the model to generate observations that appear to have been drawn from the population or the data. So that gives us some pretty desirable outcomes. So and he speaks to things like accuracy, so that you basically can make some assumptions, and some of these are a little loose. And we do have some challenges with some of the approaches, like naive Bayes, and we'll talk about that in a bit. Make some assumptions that aren't always real in the real world. So when we talk about the idea of representation learning, This is a way of trying to model higher dimensional um, things in a simpler way. And so we may do something where we describe them in a lower dimensional way. So here we're dealing with relatively simple objects with some lines and some grayscaling to denote surfaces, right? So these are cylinders or biscuit tins, as the story goes, and so that we can train upon these in a simpler way, and then be able to do things against a higher dimensional image. And so the idea is that we can then kind of describe, be able to realize something from the data set can be described in a simpler latent space. But it's not as easy for a machine, right? We do it fairly easily because it's kind of variations on the same thing. But you always got to remember with especially things like image processing, you're dealing with of essentially one big array of numbers that represents those pixels values, maybe even 3 numbers per pixel or more, depending upon how it's being actually encoded. And so you don't necessarily know about proximity from the image unless you know the width of the image, and then you can figure out who's above and below me and beside me diagonally. Those are harder things to figure out. And to make sense of that, it's not intuitive, generally speaking. And so some key terms in order to understand some of the concepts that you're going to be introduced in the chapter is, so the sample space consists of all events. So that's kind of like a way of looking at the sample space. The probability density function that maps events to probability. So you look for the likelihood of something essentially being in the sample space. The likelihood measures the plausibility of the event, and I just kind of used that term. So how likely is something to occur? So how likely is that to be that, so to speak, or what are the odds of, or what is the chances? We'll use those terms, but it's not quite probability, but you think of it that way, but it's more like likelihood. And then the idea that what we're trying to accomplish with generative modeling is we can say that it's a form of the essentially doing maximum likelihood estimation, and we're trying to find a value for those parameters that maximize the likelihood of observing the given data. So broadly speaking, possible approaches to the generative model taxonomy is explicitly model the density function, but constrain the model in some way so that the density function is tractable. In other words, it's something that you can actually do or can solve for. A lot of these things without the way of kind of simplification of the problem, it's just not possible to solve. And then another sort of approach is to implicitly model the density function through a stochastic random process that directly generates that data. Throughout the term, we'll be going through some kind of the general landscape and where these chapters fit together. Chapters 3, 7, and 8 kind of fall into that approximate density sort of approach, as well as then 5 and 6 talk more about tractable density. And then for implicit density is when we get into things like generative adversarial networks, which are some pretty cool things. So with that, welcome to the first unit or the first chapter that we've talked about. I wish you well, and I look forward to continuing our learning journey on this course, this topic.